So hello everyone, I'm Yin Huai from Databricks. So today I'd like to talk about Catalyst, the Apache Spark optimizer. So before I start, let me introduce myself briefly and also my company. So I'm a software engineer at Databricks. I'm an Apache Spark committer and a PFC member. I'm one of the original developers of Spark SQL. So pretty much I started to work on Spark SQL after Michael started the project. And before I joined Databricks, I spent several years at Ohio State University working on data management problems. So regarding Databricks, the company is founded by people who started the project Spark at UC Berkeley in 2009. And at Databricks, our mission is to make big data simple. And what we provide is a unified analytics platform built in cloud, powered by Apache Spark. All right, let me start my talk. So in Spark SQL applies structured view of data from different systems stored with different kind of formats. It provides high-level structure APIs like SQL, data frame, and dataset. Spark SQL has been the foundation of lots of recent innovations and enhancements made to Spark, like ML pipelines, structured streaming, and the graph frames. And Spark SQL will keep serving as a foundation for future innovations and enhancements. With the structured APIs, users can write programs in a more concise way using high-level programming interfaces like SQL, data frame, and dataset. These programs are used to describe what data operations are needed without specifying how to execute those data operations. For example, let's say we want to calculate the average age of every department in an organization. With structured APIs like data frame and SQL, we can use a very short line to describe what kind of result we want without specifying how to get the result exactly. However, with unstructured APIs like RDD, we have to use more instructions to explicitly specify every step of the calculation. And also, the program is harder to read. And here, you may want to say that structured APIs will limit what can be expressed because structured API enforces contracts and makes clear what the output of an operation will be. But however, in practice, even with those limitations, we can still accommodate the vast majority of computations using structured APIs. And more importantly, when we limit the space of what can be expressed and enforce contracts, we're enabling tons of optimization opportunities. Let me show you a simple example. So here, this figure shows the runtime performance of aggregating 10 million integer pairs in seconds. By taking advantage of different kinds of optimization opportunities, programs writing in SQL and a data frame can run much faster than program written in RDD. So this looks super cool, and we can see like structured API enable lots of optimization opportunities, but there's a question. Because with structured APIs, users do not specify how to evaluate those data operations. So how should we take advantage of optimization opportunities exactly? The answer is quite simple. To take advantage of optimization opportunities, we need to get an optimizer that automatically finds out the most efficient plan to execute the data operations specified in your code. And in Spark, Catalyst is such an optimizer. So Catalyst serves as a bridge between programs writing in the high-level programming interface and the optimized execution plans. So in the rest of my talk, I will give you an introduction about Catalyst. I will introduce the core concepts of it and help you understand how it works. And at the second part, I will walk through an example to give you a taste on how to customize Catalyst without even changing the code of a Spark. And later this morning and tomorrow, there will be talk about specifically focusing on recent enhancement made to Spark based on Catalyst. So for example, later this morning at this room, there's a talk from Facebook talking about improved backend support. And tomorrow, engineers from Databricks and Huawei will give you a deep dive on custom-based optimizer, which is coming in the Spark 2.2 release. So all right, let's look at how Catalyst works. At high levels, Catalyst has an internal representation of a user program called a query plan. The high-level programming interface in Spark are essentially the public APIs to create those query plans. Once we have the initial query plan, through different kinds of transformations, the Catalyst will convert the initial query plan to an optimized version. And finally, through Spark SQL's code generation mechanism, the optimized query plan will be translated to a DAG of RDDs, which are ready for executions. At its core, Catalyst defines the abstraction of a user's program as trees and the transformation from one tree to another tree. So now let me introduce these two kinds of concepts to help you understand how Catalyst works. So let me start with tree. So for a program built using high-level programming interface, for example, this SQL query, we need a way to describe how to generate a new column using the input column. And in Spark, expressions are used for this purpose. In this SQL query, we can find 5 expressions. Like for example, 1 plus 2 plus T1 value, this is one expression. And in Spark, the columns are also represented by the expression, and we call those attributes. An attribute can represent a column of a data set, and for example, T1.id at here, or a column generated by a specific data operations. Like for example, the attribute we at here represents the result of 1 plus 2 plus T1.value. So we can use expressions to represent operation of generating a new value from input values. We also need a way to describe how to generate a new data set from input data sets. And in Spark, query plans are used for this purpose. A query plan is used to describe a data operation like aggregate, join, filter that generate a new data set using different kind of input data sets. And a query plan uses one or more expressions. And here is a query, and you can see this is an example query plan. You can see we have a scan node, join node, filter node, project node, and an aggregate node. They all represent specific data operations. And in Catalyst, there are 2 kinds of query plans. The first kind of query plan is called a logical plan. A logical plan describes computation on data sets without defining how to conduct a computation. The logical plan gave us a nice abstraction of user's program and allow us to freely transform the query plan without worrying about the detailed execution details. And every logical plan has a list of output columns, and they are represented by attributes. And also, every logical plan has a property called constraints. So the constraint is a set of invariants about the rows generated by a query plan node. So for example, in this case, we have one of the constraints is T2.id is greater than 50,000, because if you look at the query plan, this condition is actually part of the filter. So the output of that filter operator will satisfy this condition. And finally, we have statistics built into the logical plan, and the statistics can describe the size of the plan in the row or bytes. We also have per column statistics. For example, the max value, mean value, number of distinct value, and the number of raw null values. So this is a logical plan, the first kind of query plan. The second kind of query plan is called a physical plan. A physical plan describes computations on dataset with specific definition on how to conduct the computation. So a physical plan is actually executable. You can actually run it, and it will evaluate your data and give you the result. So for example, this is an example physical plan. As you can see, the drawing node here is called a sort-merge drawing, which means the sort-merge drawing algorithm is used by these physical drawing nodes. So now I have introduced how Catalyst abstract user programs as trees. Let's look at the transformation, which is the mechanism used to convert an unoptimized tree to an optimized tree. So transformation in Spark are pure functions, and we do not mutate the tree, but instead we produce a new one if the transformation applies. So in Catalyst, there are two kinds of transformations. The first kind of transformations are used to transform a tree to another tree without changing the type of the tree. So through this kind of transformation, we can transform an expression to another expression, a logical plan to another logical plan, or a physical plan to another physical plan. The second kind of transformation are used to transform a tree from one kind to another kind. And specifically in Spark, we use this kind of a transformation to convert a tree in a logical plan to a physical plan. So I will start to introduce the first kind of transformation and then talk about the second kind of transformation. So in Catalyst, a single transformation is done by a single rule. And the rule is implemented by a function called a transform. This function is associated with every tree. So you can use it with expression, or you can also use it with query plans. So for example, here we have an expression tree, which represents 1 plus 2 plus t1 dot value. And by applying a transformation, we can evaluate 1 plus 2 and convert this tree to another kind of tree, which is just 3 plus t1 dot value. And these two trees are equivalent because they produce the same kind of result. And for this specific example, we call it a constant folding in the Spark's optimizer. And a transform is defined as a partial function. So a partial function is a function is only defined for a subset of its possible arguments. So for example, let's see this piece of code. So this code will only get triggered when we are adding two integer like constant values. And the case statement here determines if the partial function will be triggered or not. Okay, so this is pretty cool. We can write a single transform function to transform a tree to another kind of to a tree in the same type. But oftentimes, we want to combine different kinds of transformation rules to make change to the tree, which cannot be done by a single transform rule. So in Catalyst, we can easily combine multiple rules together. And let's see an example first. So here, we are drawing two data sets, T1 and T2, and then we will have a filter to filter out the drawing result, and then finally we'll project T1.id, and another column we want to project is 3 plus T1.value. So first, when we look at this query plan, we'll figure out, we'll find, okay, the T2.id, that condition is actually only related to the table T2. So what we can do is we can push down the predicate through the drawing. So basically, we want to evaluate the predicate first. That will reduce the input side of the drawing and speed up the drawing performance. So this is called predicate pushdown. So we first push down the filter through the drawing and evaluate that first. And then after we finish this transformation, we find, okay, we only need 3 columns actually. From the T1, we only need the column ID and a value. From T2, we only need a column called ID. So what we can do is to add 2 project nodes to explicitly select the 3 needed columns. So with this change, we're able to avoid reading unnecessary data if the underlying started format are columnar formats like Parquet or ORC, which can actually reduce a lot of I/O cost. So, all right, so that's pretty cool. We combine these two rules together and then convert a plan from the left-hand side to the right-hand side, and which is like more optimized version. So in Spark, we use a mechanism called a rule executor to combine multiple rules. A rule executor transforms a tree to another tree with the same time by applying many rules defined in batches. So you can see in Spark we have different kind of batches of the rules, and every rule is implemented based on the transform. And there are two approaches to apply rules. And the first approach, basically we just apply the rules in a batch over and over again until the tree does not change anymore. So in Spark, we call this approach a fixed point, because we want to like iterate to like change the tree until we converge. The second kind of approach is basically we apply all the rules in the same batch just once and got them all triggered, and then we're done. So this approach is simply called once in Spark. So all right, so that's about the first kind of transformation. So now let's look at how we transform a tree to a different kind of tree. Specifically, let's see how Spark transforms a logical plan tree to a physical plan tree. So in Spark, a logical plan is transformed to a physical plan by applying a set of strategies. So every strategy uses pattern matching to convert a logical plan to a corresponding version of a physical plan. So here is an example strategy. You can see that this strategy is called basic operators, and what I'm showing here is basically we're converting the logical project node to the physical project node, and we also convert the logical filter node to the physical filter nodes. And the physical node contains the information on how we actually execute this operation and generate the result. So, but oftentimes a single strategy may not be able to convert all kinds of logical plan. So what we can do is we will call plan later. The plan later will actually trigger different kind of a strategy. So we combine all of those strategies together to convert a logical plan tree to a physical plan tree. So now I have introduced trees and the transformations in Catalyst. Let's see how Catalyst exactly transforms a user program to an optimized version. That is, and the right version is ready for execution. And this process is done through 3 steps, so which are analysis, logical optimization, and physical planning. So for the analysis, we use a rule executor to implement a bunch of transforms to convert a tree from unresolved logical plan to a resolved logical plan. So that here, this changes from unresolved to resolved is actually Spark will use a catalog to find where data sets and columns are coming from and what are the type of them. And after we got the resolved logical plan, we will use a rule executor. We have a different kind of we have a rule executor implement different kinds of transform rules to transform a resolved logical plan to an optimized logical plan. So this is the step of logical optimization. And finally, from optimized logical plan, we want to convert that to a physical plan which is ready for execution. So this is done in the step of physical planning. The physical planning step has 2 phases. The first one is we basically use strategies to transform an optimized logical plan to a physical plan. And in the second phase, we use a rule executor to transform those physical plan again. And we want to make the plan ready for execution. like for example, we will figure out how we shuffle the data, how we partition the data, and what kind of columns are used to partition the data. So now we have learned how Catalyst works, so let's put what we just learned in action. So what I'm going to show you right here is to use Catalyst API to customize Spark without changing the code of Spark. So basically, I want to show you an example to plug in a special query planner rule to speed up a certain kind of queries. So let's say we have two data sets. The one data set is table A, another data set is table B. So they are quite simple. We use the range function in Spark to generate them. So they all represent like a bunch of numbers. So for table A is a data set of integer, they're like in total 20 million like integer numbers. For the table B is another data set, which is like relatively smaller, is 10 million integer numbers. So what we want to do is quite simple. We want to join these two data sets, and then we want to calculate the number of join output. So you can see the query is quite simple. We have table A drawing table B on their common column, which is called ID. And after that, we want to do a group by, and we want to calculate the count for the entire result data set of the drawing. And finally, in the Spark, we will call result.show to trigger the execution. So usually, this operation will take about 4 to 8 seconds in the Databricks Community Edition, and which is running a mini cluster. So this is actually quite a simple query, but it takes a relatively long time because there are just lots of numbers. And if we look at the query plan, you can see that we first need to shuffle the data because we want to join based on the value of ID, so we need to shuffle the data based on the value of ID. And after these two data sets got co-grouped, so we will sort them and do the join. And the join algorithm here is the sort merge join. And by the way, you can get this plan by using explan method on the data set or data frame. So you can see that here, the exchange, sort, and sort merge join operator are actually quite expensive. You need to shuffle the data around, you need to sort the data, and then you need to do the join. All of those are quite expensive operators. So how should we optimize this query? So we want to exploit the structure of the problem. So actually, for this kind of query, we're just drawing two intervals. So the result will be the intersection of the interval, right? So let's say we have this data set A and data set B. So when we join them, we just need to get the intersection. So what we can do is to write a special query plan rule to match the cases when we join two intervals and calculate the intersection directly and put that back into the query plan. So instead of doing a shuffle, sort, or join, what we're going to do is just figure out, okay, we have this kind of case, we just replace the result with a intersection, which will be much faster. So right here you can see that the case, the highlighted part is a condition used to trigger this rule. So you can see we want to match the case of when we're drawing two intervals, and then here we'll just calculate the intersection. And once we got the intersection, we put it back into the query, and then we're done. So, and after we have this customized rule called interval join, we can hook it into the Spark. And we don't need to change the code of the Spark. So what we can do is hook this strategy through the experimental.actual strategy extension point provided by Spark session. And then this rule will be part of the Spark's query planner. And we'll run it. It will take about less than 0.5 seconds to finish. So this is like a really good speed up because we don't do the shuffle, we don't do the sort, we don't do the drawing. We just get the result, put that in the query plan, and we're done. So if you look at the plan, it's actually pretty straightforward. Instead of having shuffle, drawing, and sort, we got the intersection directly. We put it back into the query plan, and we generate the result directly without doing those expensive operations. So those are pretty cool. So great. So we have seen how we can plug in planner rules to Spark without changing the Spark's code. So I also encourage you to actually try it out, and if you have any good idea, so I'd like you to contribute to Spark. So let me show you an example. This is a patch for Spark 3462. So the code is a little bit more than 100 lines. It's like 110 lines. So, but what it can do is actually make a user's query from never finishing to finish in 200 seconds. This is like tremendous speed up because the original version didn't run at all. So, and in the past 2 years, more than 200 people have contributed to the component powered by Catalyst or the Catalyst itself. So I encourage you to play with it and try the extension point and contribute your idea to Spark. Because oftentimes we see like very small changes made to Catalyst that can provide a huge performance speed up to like some certain kind of user's query. So finally, if you want to quickly prototype your customization of Spark, or you just want to use Spark to solve your data problem, I'd encourage you to try out Databricks. And you can sign up for our free trial or sign up for our free community edition. And we at Databricks, we provide a unified analytics platform, and it's a collaborative cloud environment. And I encourage you to try out our upcoming, the Databricks Runtime 3.0, which is powered by Spark, and we have extension optimized for cloud environment, and we have the optimized caching and the optimizer layer, and we also provide the enterprise security features. So, all right, that's all my talk. So I will be around after this talk, or you can also find me at my office hour at the Databricks booth from 3 to 3:40 p.m. So thank you so much for your time. Hope you enjoyed the show. All right.
We've got about 3 minutes for Q&A. So if you want to ask any questions, please put your mind on the other side of the aisle. Feel free to ask any questions. We've got a couple of minutes. If not, stop by at the Databricks booth and ask him any questions. All right, thank you.
All right, thanks so much.